Okay, thank you. Okay, so I will first start with some introduction, and then we'll get the actual content of this class started. Okay, so first, my name is Zhou. I'm a professor in computer science here at Berkeley, and also a co-director of a campus-wide center called the Center on Responsible Decentralized Intelligence. So I'm the instructor for this class, and also we have a guest co-instructor, Xingyun Chen from Google, who is also a Berkeley alum. She's my former student here, teaching this class together. And also we have our great TAs, Alex and Sihun, and also we have our great readers, Tara and Ashwin. Okay, so this is the teaching staff who will be working together with you this semester. Okay, great. So everyone's here. Everyone has been seeing the exciting growth of large language models. The speed of advancement is just astonishing. However, these large language models, they operate in a fairly simple manner. They take text inputs and produce text outputs. So what we will cover in this semester in this class is the next frontier, large language model agents. So instead of just taking text as input and produce text as outputs, here we use a large language model as the key brain for reasoning and planning for the agents and enable the agents to interact with external environments, observe the environments, and take actions in the environments. And the agents will be using external tools and also external database and knowledge base and so on for retrieval to help the agents to perform these tasks. And the rich capabilities of these large language models makes these LLM agents very flexible and they can easily operate in diverse environments without much particular specific training. And these LLM agents, they can interact with different types of environments, including, for example, surfing the web through different APIs online, and they can also be embodied even in a robot and operating in a physical world. And they can sense the environments through different types of inputs, even in the multimodal setting, even including various sensory inputs, and taking actions in these diverse environments. And through this interaction with the complex and diverse environments, they can update their memory, they can learn to use, they can interact with humans, and they obtain grounding through this interactions as well. And these agents not only just interact with the environments, they can interact with other agents through multi-agent interactions and collaboration, including humans as well. And these multi-agent collaboration can help agents together to solve even more complex tasks. So why is LLM agents the next frontier? Why do we need to empower LLMs with the agent framework? For a number of reasons. Solving real-world tasks is never just in one go with text inputs, produce text outputs. Oftentimes it involves a trial and error process. And leveraging external tools and the retrieval from external knowledge can help expand LLM's capabilities. And more importantly, this dynamic agentic flow, this agent workflow can facilitate solving complex tasks through enabling task decomposition, allocation of subtasks to specialized modules, division of labor for project collaboration. And throughout the course, we also see that multi-agent generation can help inspire better responses. Even though agents has been a fairly recent development, we have already seen agents helping transform different application domains through wide-ranging, including education, law, finance, healthcare, cybersecurity, you name it. And the development is really exciting and is fast improving. There are many different leaderboards for different agent benchmarks that you can see online, and you can see the really fast improvements on all these different agent frameworks. So overall, to better enable agent deployments, there are a number of key challenges that we still need to address. So first, we need to improve the reasoning and planning capabilities of agents. Agents tend to make mistakes when performing complex tasks end-to-end, and it's important to improve the reasoning and planning capabilities. And also we need to improve embodiment and the learning from environmental feedback for these LLM agents. LLM agents are still not efficient at recovering from mistakes for long horizon tasks. We need to further develop methods and capabilities for continuous learning and self-improvements for these LLM agents, and also improve multi-model understanding, grounding, and world model capabilities of these agents. And also, as I mentioned, multi-agent can really help agents to provide better solutions for tasks, and developing theory of mind helps multi-agents to better develop as well. And safety and privacy, these issues are also very important for agents. LLMs are susceptible to adversarial attacks, can emit harmful messages, or leak private data, and so on. Solving these challenges are also really important for deploying LLM agents safely in the real world. And also enabling human-agent interactions and ethics, how to effectively control LLM agent behaviors, and design interaction modes between humans and LLM agents to best enable LLM agents to serve human needs is also really important. So to help students learn and better develop methods to address these challenges, the course has been designed to cover a broad spectrum of topics, actually throughout the different layers of the agent's framework and also the domains. So first, in the class, we'll cover key model capabilities, including reasoning, planning, multi-model understanding. We'll also cover popular real-world LLM agent frameworks to enable students to learn how to better design agent applications and use various agentic flows easily. And this will help students to also learn to use our agent frameworks for workflow design to use retrieval augmented generation RAG and multi-agent systems. And we'll also cover a number of exciting application domains using these LLM agents, including software code development, workflow automation, multi-model applications, and enterprise applications. And finally, we'll also cover important topics on our agents' safety and ethics. To cover this wide-ranging topics, we have assembled an amazing team of guest speakers and researchers to cover these topics. So the class will be led by me and Xinyun, and we have this amazing crew of guest speakers to help cover these important topics in class.
Before the talk, I want to ask one question for everyone. So what do you expect for AI? It may take a few seconds. Think about it. So I can imagine many different answers, like solve the hardest math problems that humans cannot solve. For example, even tell you how to solve, right? Or discover new scientific theory, or even solve AGI. My background is machine learning. I don't know in the current days, still many people study machine learning course or not, because it's like transformer is all we need, right? As a machine learning person, I have a little expectation about AI. AI should be able to learn from just a few examples, like what humans usually do. In the past decades, the machine learning community spent great efforts to develop data-efficient methods like semi-supervised learning, active learning, kernel machine something. And if you look at newspaper in the past decade, the people are always excited about 1-point, 2-point gains in the as oral paper. So in practice, actually, I never saw data-efficient approaches. I would like to see mission failed. Don't feel bad about it. I'm the person who feel bad because I started machine learning almost 20 years ago. Or after seeing the failure, actually that motivated me to think a different problem. What's missing in machine learning? So I sort of tried them for years, and finally, I found out the answer: reasoning. In the current days, in particular for people in the course today, the answer seems so obvious, right? Because this lecture about reasoning. Humans can learn from just few examples because humans can reason, not because of data statistics. Sounds so straightforward. Let's start from a toy problem. In my research, I usually prefer a very simple problem, but it contains all the detail, all the challenging places. So this toy problem is called a last letter concatenation. If you are familiar with neurosymbolic literature, you will find similar problems. So for this problem, given a people name as input, the output will be the concatenation of the last letter of the first name and last name. For example, like Elon Musk. The last letter of Elon is N, the last letter of Musk is K. So the output is NK. It's so simple. And if you have this problem, a few years ago, you probably would try to solve it by a machine learning model. For example, you could use transformer model. Is Y is a decoder, the other is encoder. Y is an encoder, the other is a decoder. Right? And then you will find that, okay, you will probably need tens of labeled examples to train the model. And finally, you can get an accuracy like 85% or 9% or something. Now it's interesting to think about machine learning methods. For such a simple task, simple for humans, okay. And if the method requires a vast amount of labeled data to learn, and would you like to call it as AI or not? AI means artificial intelligence, right? I suppose an intelligent model should be able to learn this task, just use one or two examples. Now let's see how this problem can be solved by using large language models. I suppose most people know large language models, but Professor Dan told me to explain what LLM are. Okay, LLMs is a transformer model trained to predict next word. For example, given the text, AI is the future. We mask future, just use AI as the input. We let the model predict what will be the next word. If the next prediction is not the word future, we need to adjust parameters to make the prediction correct. In machine learning, that's called backpropagation. Of course, yeah, you can train your model with many sentences. For example, you can use all text from the internet. If you don't want to go to details, you can simply think of training LLMs as training parrots to mimic human language. Actually, I tweeted this sentence, and one guy replied to me. He said he's very curious about training parrots. He's looking for a job. Once we train this model, okay, and then we can just mimic the process of the training. Because the training is about predicting next token. We can use whatever as input and to see what will be the output. The model just predicts next token, and then you can input the generated token, and you can use the input generated token and predict next token. That's how to get an answer from LLMs. And for this problem, we can simply concatenate all the examples we have had as the input, and also concatenate with a test example, Barack Obama here. We can try this as use any LLM and see what happened, and probably can see you can run answer here. Is called CK. Of course, it's not correct, right? Because K is the last letter of Barack, and A is the last letter of Obama. The output should be a KA. So it's wrong, right? The problem, this is called few shot prompting. It's just a mimic of a machine learning process. Instead of training model, we just use the examples as the input. That's the only difference. In the coming days, we know how to fix this prompting idea. We just need to add reasoning process before the answer. Like we just add the explicit process here. The last letter of Elon is N. The last of mask is K. Concatenated NK. This is called NK, like that. It's called a reasoning process. And similarly for Bill Gates. And now we use this as the new input, and you will see, okay, we get a perfect response from the large language models. So even like humans, one demonstration is enough to get an accuracy of 100%. That's exactly what I looked for. We cannot imagine any machine learning method can achieve this perfect generalization here. There's no way. But by the way, don't overrate what I said about machine learning. Machine learning is just super useful and important for doing research. In the kind of days, I saw many naive mistakes from social media news, even from the papers in the CoT conferences. All the naive mistakes mostly from people who have no expertise on machine learning. They just randomly try different ideas. It's interestingly, this kind of idea of adding intermediate steps has been proposed many years in the literature. So this is the amazing paper by researchers at CoT Reasoning, published in ACL 2017. So in their paper, they use natural language rationale to solve math problems. In their paper, they even derived the final answer through a series of small steps. And then they trained a 7-to-6 model from scratch. If you know channel sort of work, you'll be so surprising about this paper, right? The authors are just like time travelers. They know how to make a different approach. In 2021, a team in the OpenAI published an amazing data set called CS294. They followed the idea in DeepMind paper in 2017. In this data set, every problem followed by intermediate steps, a solution, and also final answer. And this team created this amazing data set and used that to fine-tune GPT-3 model. They greatly scale up the work by DeepMind in 2017. Even in the same year, 2021, a group of researchers in Google Brain, now part of Google DeepMind, published the work like Show Your Work, scratch pads for intermediate computation with large language models. They discovered the similar ideas independently, but in the domain of program synthesis. That's why they used abstract symbols here instead of using natural language. In the context, probably many people know our word chain of thought prompting. And the chain of thought actually, literally, chain of thought is not a term we invented. It's just common English phrase. It means multi-step reasoning. So in this work, we extensively evaluated prompting with individual steps and showed amazing results on almost every NLP task. So let's put all the papers here together. In 2017, CoT Reasoning published a paper, Training with Intermediate Steps. In 2021, and people published papers, fine-tune LLMs with intermediate steps. In 2021 and 2022, and prompting with intermediate steps. How do you see, okay, which part is more important? You can see here, actually, it doesn't matter if you are trained or fine-tune or prompt model. What really matters here, intermediate steps. That's the key. So let me summarize here. Regardless of training, fine-tuning, or prompting, when provided with examples that include intermediate steps, LLMs will generate responses that also include intermediate steps. Okay. Given intermediate steps, we may ask a question. Is it helpful to introduce reasoning strategies in those examples? For humans, when they solve a problem, they could have a strategy for solving. So this, so here's work from our team is this most prompting. In this work, we enable easy to hard generalization by decomposition. Probably many people saw this famous book, How to Solve It, by Korea, a classic book for math education. So there's a chapter about decomposition. So if you go to details, you may lose yourself in details. Yeah. Now let's see what is the difference by decomposition. So given this math problem here. So by the way, so in this talk, the math is kept at the elementary level. So every time when I give a talk, before actually my daughter also gave my talk, and she reviewed my slides to make sure she could understand. She's in the 5th grade now. And they said ESR has 3 apples. Anna had 2 more apples than ESR. How many apples do they have together? Okay, well, we see the difference is that, okay, we first show large language models how to break down this problem to solve problems and then solve them one by one. Yeah. And that's why I call least to most, from least to most complex problems. It's very simple idea, but surprisingly powerful. So that's just like humans, how to decompose complex tasks into simpler tasks. So this is a scan task for compositional generalization. You can look at examples here, give a natural language command, and we need to translate to a sequence of actions. And that could be executed by robots, something like that. So if you use least to most prompting, we can get accuracy 99.7. So we just use 0.1% demonstration examples. So why I chose this task? Actually, I knew this task from Xinmin. She's here today. And she invented a beautiful approach to solve this task many years ago. When I looked at this task, I was really surprised because it looks so straightforward for humans. Why it could be so difficult for machines? Finally, we can make it by LLMs. And this is another task with CF2, test to code. Again, with a compositional generalization task. I don't know if anyone knows the concept compositional generalization. Roughly speaking, the task examples are more difficult than training examples or prompting examples. So, for example, for the task code problems, the task problems we need a longer code snippet. Here, where our approach is a little bit changed a little bit, it's called dynamic least most prompting, and we just use 1% data and achieve the perfect great results, way better than the solar results in the literature. And the solar results in the literature are actually by specialized architecture design and training. And they use, of course, all the training data set. Yeah, so far, any question here? Otherwise, I'll go to the next section. Yeah. Okay, I suppose this part is quite familiar for everyone. I have 2 kids. My daughter is 10 years old, and my son is 7 years old. Actually, when the Chains of Prompting paper came out, I heard a very interesting conversation between my daughter and my son. And my daughter asked her little brother, so what's 17 times 3? The little brother said, I don't know. And then she asked, what's 10 times 3? 30. What's 7 times 3? 21. So what's the 17 times 3? Oh, yeah, I know, 51. And the funny thing is, my daughter shouted to me, Daddy, channels of prompting also works in my little brother's brain. Okay. Now, okay, one may say, okay, why intermediate steps are helpful? Okay. So one may say, okay, that's so natural for humans. But if we are doing research, we have to think deeper. That's just something similar that our large language models are just machine learning models. We have to understand what happened. And this year we have work published at ICLEO 2024, and I collaborated with brilliant theoreticians from Stanford. And in that work, we give a rigorous mathematical analysis. Okay, so here are the key results. Transformer generating intermediate steps can solve any inherently serial problem as long as its depth exceeds a constant threshold. I have to emphasize again, constant. That means independent of your input. However, if a transformer generating direct answers either requires a huge depth to solve or cannot solve at all. Yeah, please check the statements again. Then I'm moving to the next slide. Probably can see tons of practical implications of this theory. Yeah, if you couldn't solve a problem, you may think about generating more intermediate steps. And also, probably you could call some external tools like search to help intermediate steps. Right. So I studied in this LLM agent course, many people talk about how to use external tools. And you can think about how to diagnose in LLM failures and limitations. Yeah. So actually one of my big fun is to find problems my daughter can solve in seconds, but LLMs fail. Yeah. Okay. So far we have talked about how to use examples to trigger LLMs to generate step-by-step reasoning. So one wonder, is it possible to trigger reasoning without using examples? Here's an amazing work. Actually, when this paper came out, I thought it was a joke. It turned out not. And then I was inspired a lot by this work. It's called Let's Think Step by Step. So given this question, okay, we don't need any examples. We just need to say, let's think step by step. And the model can generate reasoning steps. Yeah, it's really cool, but usually, the zero-shot approach, that means the zero-shot means there's no demonstrated examples. It's worse than few-shot. So one may wonder, okay, if we can have an approach, it's still zero-shot, but can do much better work. So this leads to our another work is called LLMs as analogical reasoners. So again, this beautiful book, How to Solve It, and actually, so in this book say, okay, how to do analogical reasoning in solve math problems. So we will see a new problem. You first ask your question, do you know a related problem or methods or strategies? Yeah. So after my talk, probably you're going to try to find this book to read and write another paper. So this, I really like the code from Banach, yeah. If you studied function analysis, you will know Banach space. And I was really amazed by that last sentence. The ultimate mathematician is one who can see analogies between the analogies. Of course, actually, I showed a sentence here to let you know how far we are from AGI. So given this simple problem, okay, of course you can see, okay, let's think step by step, but now we can see a different way. Okay, we call a related problem and then solve this one. Okay, you can see that actually, indeed, we call relevant examples and the knowledge is here, but those problems are exactly the same problem, but they are useful. That's amazing, you know. And we found that actually, which of course we tried benchmarks and see it works really well. So you can see that the last row is from Analogical Reasoning by prompt. Of course, you can optimize the prompts by yourself, get better results. The most important thing here is see that it's much better than just see let's think step by step. Let's think step by step here means zero shot CoT. Yeah. And even this approach outperforms manual CoT here. I think the main reason is that when you use this approach, the model automatically generates related equations to each different problem. This results on a big bench. Yeah. So it was a great performance. And the results on CoT forces, compatible programming. Yeah. If you are interested in compatible programming, you could try this approach. So what we didn't do here is about scaling. You can even you can search the web from all related problems, knowledges for the problem you will solve. So the key idea here, adaptively generate relevant examples and knowledge for each given problem, instead of using a fixed set examples as a manual channels of prompting. Okay, now we can see that, okay, we can use few short examples to show the model how to do step-by-step reasoning. We also can do zero shot without using any examples, just see that step by step. Now we could ask another question. Is it possible to trigger step-by-step reasoning even without using any prompt? Let's think step by step. You could say, okay, all the models in the country are just like that, right? You're right. But they did instruction tuning or something. That means they already used many examples in the data mixture for training or tuning. So, yeah, we found the answer is yes. This in our recent work, channel CoT reasoning without prompting. Without prompting, that means without saying anything, just give problem to the model, even for a pre-trained LLMs, not tuned. So let's look at the example here. I have 3 apples. My dad has 2 more apples than me, and how many apples do we have together? For this example, we see the approach actually is very simple. At decoding at the first step, we look at all the possible tokens. Here I listed 5 tokens here. Okay. So we started the first 5 tokens and then continue graded decoding. Okay. For the first one, is a 5 apples. Okay. The first token is 5, and the next token was 5 apples. And if you use token 2 token, so it's I, then the full generation will be, I have 3 apples, my dad has 2 more apples, then me and Sophie has 5 apples. Yeah, it's correct. Yeah. And I see that. So that's very interesting, right? So we didn't see anything about reasoning here, but the model can do some reasoning if we started from different tokens. Here's another example. You say, okay, was Nicholas Cage born in even or odd year? The first one say, okay, Nicholas Cage was born in odd year, that means Nicholas was the first token. And for the second one, that's just even and then period. The third one is odd, then period. Okay. Now probably say, okay, if the indices, the model could have had chain of thought in their response. The problem is how founded. I may say, okay, you can take a longer sentences. Right? Longer sentence means the model could do some reasoning steps. Actually, a surprising thing is to look at the probability of the net on the token of final answer. If you look at the probability on the first row here, and Nicholas Cage was born in an odd year, and the probability is quite low. And however, if you see, if there's a reasoning part, like the last one, Cage was born in 1964 and an even year. There's a reasoning process here, and then probability finally jumped to 0.98. That's amazing, right? It seems that the model is so well calibrated. I was really surprised at seeing those probabilities. See that like 2 and 3, if the model say even or odd, right, the probabilities are really low. So key observations, and pre-trained LLMs have had responses with step-by-step reasoning among generations started with the top key tokens. We don't need to use any prompts here. It's not needed. And higher confidence in decoding the final answer when a step-by-step reasoning path is present. So here is a comparison between graded decoding and the chain of thought decoding. We see that the chain of thought decoding performs much better. Yeah, so far, any question here? Now let's move to the next topic, right? Generating intermediate steps are helpful, even really helpful, but any concern on generating intermediate steps instead of direct answers? Any concerns? Okay, yeah.
So this method doesn't essentially give a lot more things
So probably I would say depends on your problem, your need, yeah. So actually in the candidates, we need to always keep in mind that LLMs are probability models of generating next tokens. They are not humans. No matter if I use my case examples or not, keep this in mind. So it's a probability model. So let's see what LLM does in decoding. So it's actually argmax probability of reasoning path and the final answer given the problem. However, what we want is argmax probability final answer given problem, right? That's what we learned in machine learning. This doesn't mean reason path is not important. I just say final answer. We have to make sure final answer is correct and then look at the reason path. They are not aligned, right? The two different objectives. Okay. Now let's look one step further. Okay. The probability of final answer given the problem. How to compute it? We should sum over all possible reasoning paths. Okay. That's how the probability is computed from our course we'll learn, right? So given a math problem, you could find different solutions which lead to the same answer. Yeah, we need to do the summation here. And then, okay, how to compute the sum? If you study machine learning, you'll know the answer here, right? Sampling, so simple, okay. Now, this leads to our work, self-consistency. Probably many people have no self-consistency, but my talk here is I really want to let you see the underlying motivation, how we approach this problem from the first principles in machine learning. So let's look at the question here. Okay, given this math problem, and you could sample the answer multiple times, yeah, again, and then finally you see, okay, the most frequent answer is 18. Okay, well, we give a warning here is not most frequent reasoning path. We choose most frequent answer. That's a huge difference. Reasoning path here is latent variable. This idea is so simple. By using self-consistency, we simply crush solar results in the literature at that time. You can see that in doing research, we don't need to, we can, it's really just about the idea. You don't have to know a lot of things. And of course, given our explanation on self-consistency, it's about probability, it's about sampling. So imagine that more consistent results, more likely to be correct. When you look at the curves here, if the consistency is more than 80%, then the accuracy is nearly 100%. Here, quiz point one. Okay. So when the LLM outputs a direct answer without intermediate steps, we will still sample several times and then choose the most common answer. Anyone would like to give an answer here? Yeah. Okay, great. Yeah, it's one token. Okay, that's already the token with maximum probability. Yeah, okay. And for the second question, change self-consistency by letting LLM generate multiple responses instead of sampling multiple times, and then choosing the most common answer. Does this make sense? Yeah.
No.
Great. Yeah, that is no. And for both answers, we just need to follow this principle. Max probability to find an answer given problem. That's all you need to understand self-consistency. It's a very, very simple principle. Also, one of the first principles in machine learning. If you know machine learning more, probably you know, okay, this is called maximum marginal inference. Okay, so one more, okay, how about free-form answers? This is done as universal self-consistency, that machine here. So this idea is a little bit different, but related, so I put here. And given this problem, where do people drink less coffee than they do in Mexico? You know, if you look at answers, and each answer is different from others, but the most common response is two here, Japan, China, and India. Any question? Otherwise, I'm going to move to the next section. Okay. No, yeah.
What the self-consistent?
Self-consistency? Or sample your answer multiple times and then choose the most frequent answer as the output. Yeah. And next, I'm going to talk about limitations. The first one I will talk about, LLMs can be easily distracted by irrelevant context. From psychology studies, irrelevant information may significantly decrease some children and even adults' problem-solving accuracy. So I want to check if this observation holds for LLMs. So this is a simple problem here. The highlighted text is manually added with Mario's monthly rate, which is $10. It's relevant to the original problem. But you see after that the model made a wrong solution here. So actually the interesting is that, okay, if we add a prompt like ignore irrelevant context, and the model immediately notice that and make a correct one. But it's still hard to take a point back if we make the problem, make irrelevant context actually big. So even we can simply just add irrelevant sentences like the sky is blue and the grass is green or something, those nonsense. You can make this input actually long. You will see a significant performance drop across all LLMs. The next limitation I'm going to talk about, LLMs cannot self-correct reasoning yet. Let's start from a math problem again. And actually, this problem is a little bit tricky. If you look at it. And you can see that the model gave a wrong answer. And then we prompted the model with review your previous answer and find problems with your answer. Okay. And then interestingly, after reviewing, the model recognized the mistake and corrected its answer. This looks sounds amazing, right? You see, and then we see another prompt. So based on the problem you find, improve your answer. And the final answer here is correct. However, if the original answer is correct, we do the same prompt, the model could make mistakes. That's the problem. So overall, when allowing LLMs to review their generated response can help correct inaccurate answers. It may also risk changing correct answers into incorrect ones. We run extensive studies on some benchmarks like GSMK, Conversations QA, and hard QA. And we didn't notice any improvements from self-correction methods. They just make things worse. Probably you saw some improvements from the literature, they said they got improvements on reasoning. And actually, they used Oracle answers. You can see the Oracle here. Oracle means you only prompt LLMs to correct the answer when the answer is wrong. The problem is that the model doesn't know if the answer is correct or wrong. You tell them, okay, the answer is wrong, please correct it. And also, this is related to multi-agent debate. One could use multiple LLMs debate each other and to achieve agreement or consensus. And also, we try this approach. We find out actually the trick is how many responses are generated. For example, if we have 3 LLMs, and if let everyone generate a response, that will be 3. If we let them debate, that will be 3 rounds, that will be 9 responses together. So how about just do self-consistency with 9 responses and see what happened? We find that those approaches cannot outperform self-consistency. Self-consistency is much simpler. We just sample multiple times and take the most frequent answer as the final prediction. So the lesson we learned here is Oracle feedback is needed for LLM to self-correct. If so, then we lead to our work as self-debug. Self-debug naturally leverage unit tests as Oracle. It's about coding problems. You can naturally have unit tests to try. Actually, we started this work quite early, and we didn't make it a self-correcting work, and then finally we moved to the coding. And the lastly, limitation I want to talk about the premise order matters in LLM reasoning. So, in the current days, where every time we use tag reports from the archive or somewhere, and people will show great results. For example, recently a model could be reflection and it showed amazing results on GSMK. Actually, I have problems with trust those numbers. In the current days, the model all trained with all data from the internet. There could really some other problems. So one of working on my team is to generate different eval tasks. So to test the models. So here we just did a simple trick. We are given this original GSMK problem. We reorder the sentence a little bit and see if the model still can solve it. So here, in the original problem, that he lost 10 beers while getting home, and we could just move this sentence to the end and see what happened. We just did some changes for some GSK problems, and we noticed that there are about 10 points drop on solving rates across all frontier LLMs. So here are the response here. You can look at the compare response for the problem, for the original problem, and the reordered problem. So and see that the model actually just know how to solve the problem sequentially. They couldn't go back and forth. And one could say, okay, that may be related to some semantic understanding, not just about reasoning. Okay. Then we design another task. It's called logical inference. It's even more pure than math problems. You say a bunch of if then, right? Even we don't use real words, we just use random tokens here. And given the rules and the facts, and then we ask model to give inference, logical inference in the query. And the rules for the original problem, the rules are ordered according to the use in the inference process. But I will point out, not all rules are necessary for the query. And another way, we could just randomly order those rules. Okay, we only randomly order rules relevant to the query. If not relevant to the query, they just keep the original positions. And surprisingly, then we saw 30+ points performance drop across all frontier LLMs. From my personal experience, I think it's really important to design experiments when doing LLM research. So this is just like a debugging. Okay. Now let me summarize the talk here. So the first thing I talk about is generating intermediate steps improves LLM's performance actually a lot. And you can do training, fine-tuning, prompting with intermediate steps. But you can also do zero-shot analogical reasoning or some kind of a special decoding like CoT decoding I presented today. And also self-consistency greatly improves step-by-step reasoning. No matter you are from fine-tuned model or from prompting. And also a lot of limitations, like irrelevant context, self-correction, and the premise order. All those are matters for reasoning performance. So when I give a talk, people will say, okay, what will be next? What problem will work on, right? I think the most important suggestion here is, I want to say, we work on something, we put this, we shall work on AGI or solve AGI. That's not a problem. The problem is define a right problem to work on and solve it from the first principles, not just your inclusion something from principles. That's why I say machine learning is still super important here. And actually, currently, I'm organizing a conference called Conference Language Modeling with a bunch of amazing people. And this is the first ever conference dedicated to language modeling. And welcome to it. Yeah, that's it. Thanks.